Okay, good morning. Today we're going to transition from two-dimensional to three-dimensional assembly and talk about two different methods. One, the layer-by-layer method for assembling nanostructures in a sequential set of two-dimensional processes. And then we'll briefly discuss packing of crystalline structures of nanoparticles and microparticles using capillary forces induced by liquid evaporation, where it's possible to achieve monolayer structures as well as more complex multi-layer structures that somewhat resemble atoms packed in three-dimensional lattices, only where the atoms are individual nano or microstructures. First, the announcements. I just want to make sure that I met with all the project teams. If you're out there and I didn't meet with you or talk with you on the phone, please let me know by email, and we'll hope to set up an interaction. I will be out of town from later today through Sunday, so I hope we can connect this week if I didn't talk with you. There will also be another set of meetings that I'll set up for the week after this week, which is the week before the project is due. Also, as I will be out of town, there'll be no lecture on Wednesday, and our last problem set is due next Monday, April 12, at the beginning of lecture. I'm passing back the exam and problem set 3. Mustafa graded problem set 3. I graded all of the exam. Maybe if people are walking in late, run it to the back and then turn around and we'll run it back forward. And hopefully everyone who's here will get their materials. I'll put it outside my office after lecture today. Here are the statistics on the exam as announced by email. Of course, the mean is low, but I'm really not concerned about this. 57 is just a relative score. It doesn't mean that the average was a low letter grade. The exam was designed to be challenging and also to be long, and also the questions to have answers of different levels of complexity. And if you have specific questions on grading, please contact me, but also please look at the solution first. In many cases, I didn't have time to write detailed comments on every answer, but there's a number by every part of every question, and if you do have a question, just please try to compare your answer to the posted solution before you contact me. In the end, when I assign grades for the class, I really do my best to try to give the highest average letter grade I can given everyone's performance, and this only comes after I see the distribution and see how everyone has done. But this level of score is not out of the ordinary, and I wouldn't be concerned if you had a mean score, although the mean score is numerically low. And then also these are the statistics on problem set 3, so it's about an 80% average and about a bit higher than the other problem sets. And this is how the final lectures are going to shape up. Next Monday, we'll talk about self-assembly using external forces, so apply a broader consideration to the principles of force balances to understand how nanostructures assemble. And then on Wednesday, we'll talk about methods of joining structures and properties of networks. For example, transport properties of structures hooked together, mechanical properties, and thermal properties. And then, because of the way the schedule shook out, we're missing one lecture that I had last year, so I will post the slides only for the topic of nanocomposites and yarns. Unfortunately, we didn't get to it. It's not something that will be on the GCC or is any way required for the course, but I will just leave the information there for you if you're interested. And also, I think on my lab website where I have last year's lectures, you would find last year's lecture notes if that's something you wanted to look at early, for example, if the topic relates to your project. Okay, so last time we talked about self-assembled monolayers and this general process of using the interaction between amphiphilic molecules in solution and a substrate to understand how we would absorb and assemble an ordered molecular layer. And this layer had, in the ideal case, a particular order where all the molecules were standing up straight or standing at a specific angle, and you had particular domains of head groups or tail groups governed by the interactions with the substrate and the interactions between the individual molecules. And it's these balance of interactions and the relative strengths and the structure and the size and all other properties of the molecules that govern the kinetics of this process and the resulting organization that's achieved. Organization meaning the rate at which this monolayer forms, meaning the overall perfection of the monolayer, whether it's highly structured or highly defective, or consists of mixed domains where you may have highly ordered molecules and not so well ordered molecules. And we saw an example image, in this case a scanning tunneling microscope image, where these researchers had taken two types of molecules and tried to assemble them on the same substrate, and you saw in a general sense that the monolayers segregated into different planar phases. So domains of one type of self-assembled molecule, domains of the other molecule, and then areas where the substrate did not have self-assembly given the conditions that were used. And an example of a classic amphiphilic molecule used for self-assembly was the case of assembly on a gold substrate, where the strong interaction between a thiol N group and the gold surface forming the gold-sulfur bond enables sort of this versatile structure where you have a thiol N group, the SH, which reacts with the gold surface, a hydrocarbon chain of desired length and structure, and then a group at the opposite end, which may be used for subsequent bonding for other purposes, attachment of nanoparticles of particular structure, or perhaps interaction with biomolecules in the case of, for example, using a gold nanoparticle as an optical sensor by the property of surface plasmon resonance. And it turns out that the organization of these monolayers, or the self-assembly of molecules on substrates, is still a very active area of research. And in the past few years, some groups have observed and started to study interesting things that happen, for example, when we apply the principle of monolayer self-assembly to a nanoparticle surface itself. And about 5 or 6 years ago, it was first observed that if you, instead of assembling a self-assembled monolayer on a flat gold surface, if you instead assemble it on a gold nanoparticle, so otherwise the same except it has a nanoscale curvature, it turns out that when you use two different amphiphilic molecules, the molecules organize in a special fashion. In fact, in this case, the researchers were using the two molecules listed here, and regardless of the details of the molecules, it was observed that the molecules striped into these domains that sort of wrapped the nanoparticle surface like so. And you can see they kind of focused 2 points at the poles of the particle. The particle is rotationally symmetric, so the particle could be any organization, but there are energetic considerations that govern the stratification of the molecules into these striped domains. And these images at the left are of the gold nanoparticles after assembly. I think, sorry, I forgot the scale bar, but this is a range of say 5 to 10 nanometers. And by imaging the height of the layers, they were in fact able to at a preliminary level, understand the topography of the stripes. And here, this scale is from 0 to 2.5 nanometers. So if you say this is kind of half a particle, it had a diameter of between 5 and 10 nanometers. And notably, we see that these molecules consist of hydrocarbon chains terminated with the thiol group, which is known to interact strongly with gold. And there's been further research experimentally and computationally in this area, and I'm showing this because this gives us more of a qualitative understanding of what governs the organization and packing of molecules on surfaces. In fact, it's observed that the stratification of two molecules into these domains is actually driven by entropic considerations, or the desire of the molecules to be in a floppy and non-stiff state, given the structure that's designed. And if studies are done comparing particles of the same sizes, where you vary the difference in the chain length between the two molecules, then the desire of the molecules to sort of make space for themselves, or an increasing desire of that, forces stratification into these striped domains. And what we saw on the previous slide was perhaps an idealized case and maybe a somewhat idealized picture of how they would be striped into individual rows. And likewise, the diameter of the surface, or the diameter of the particle, also has an effect on the stratification, because you can imagine a larger diameter particle being more like a flat surface and therefore providing less space for the molecules to spread out, and therefore promoting this greater segregation into smaller domains or into stripes. And this is some computational modeling done of the organization on the surface, and these are STM images showing the kind of patching that occurs. And indeed, at the smallest diameters, you see this segregation, but the segregation drops out into two halves if you have equal concentrations of molecules with equal probabilities to adsorb. So aside from the specific considerations in this case, suffice it to say that the energetic interactions between the molecules and the interactions that dictate between, due to their flexibility and also to the characteristics of the substrate are important. And there are a lot of applications of studying these types of problems for example, interactions of these particles with biomolecules or interactions with the cell membrane, because it turns out that the topography and the chemical nature of this surface can affect its surface energy and can affect how it might adsorb to something else. For example, if you wanted to interact this particle with a large molecule, a protein or something, then the protein might behave very differently if it were talking to a particle of this structure where you had a chemical expression over, say, a 2 nanometer distance, to this structure where you had a chemical expression over a larger, say, 5 nanometer distance. And that's sort of where research on this topic is now. And we, in the second half of the last lecture, we talked about the Langmuir-Blodgett method, which took the principle of monolayer self-assembly and sort of modified and extended that to a case where we first organize a monolayer on a liquid surface by taking conceptually the same type of amphiphilic molecule, but now floating it on a liquid in which one end of the molecule interacts and one end doesn't. And then by controlling the packing of the monolayer on that surface, we were able to withdraw a flat substrate, such as a silicon wafer, from that liquid, and given favorable interactions between the group of the molecule that's facing the liquid and the substrate, transfer this monolayer to the substrate surface. And we saw the picture over here, an exemplary apparatus for just controlling the surface pressure and depositing the Langmuir-Blodgett layers on the surface, and also realized that given the appropriate process conditions, you could repeat this process many times. Dip and withdraw, or dip and withdraw in an area where there was no molecule, and dip again and again. And so this is another method that's been used for, indeed, decades for depositing molecular monolayers on surfaces. And there are a lot of examples of using different molecules by this process. I think one of the earliest applications of self-assembled monolayers was, in fact, coating particular chemical layers on photographic film. And more recent work has, as you may imagine, tried to extend the concept of Langmuir-Blodgett deposition to other things such as nanostructures. So now we're not talking about necessarily amphiphilic molecules that are standing on the surface, but here we're seeing pictures from a process that used the Langmuir-Blodgett method to deposit silver nanowires on the surface of a substrate. And maybe two things are different here. One, the geometry of the structures is not, molecular standing up, but it's maybe a structure that's tens of nanometers long and a few nanometers wide. And in this picture, they're making an analogy to the organization of logs on a river. So this is a picture of a river with logs that have been cut from trees, and actually how logs are transported from the forest down to the transport site is they're often just floated on the surface of the water. And here actually you see that due to the packing of the logs, they organize in an aligned fashion in a similar way that compressing the surface of a liquid in the Langmuir-Blodgett process can organize an assembly of floating nanowires. So clearly in this case, the nanowires were coated, or their native properties didn't make them soluble in the liquid solution, whereas in the case of the big logs, the density of the wood is lower, so the wood floats on the liquid surface. So you have an interaction which keeps the structure on the surface, only gravity is much more important at the macro scale than at the nanoscale. And so what the study does is they take a liquid surface and put a drop of a solution of nanowires on the top, and when the surface is not compressed, you see the nanowires are fairly loosely organized and not aligned. And then as the surface is compressed using the same kind of barrier that we saw for compression of molecular monolayers, the nanowires align like so, and align perpendicular to the barrier. And then, for example, as a substrate is withdrawn out of the solution, it's possible to transfer with some degree of control this aligned morphology to the surface of the substrate. And then, for example, they also showed that you can put the substrate through again and rotate the substrate 90 degrees and get a crossbar pattern of wires on the surface. So this doesn't have any real specific registry, but is generally an architecture where perhaps you could have, if you did this with two different types of nanowires, you'd have a large array of junctions between the two different materials. And in fact, from the results of their experiments, we see the same sort of things we would expect for molecules. So images A, B, and C are just showing their Langmuir-Blodgett trough at increasing amounts of compression. And we can see in going from image A to B to C a change in the color of the surface, which we can just relate to the density of nanowires on the surface. So as the nanowires get pushed closer together, then the surface is a bit darker in color, and that suggests the density is increasing. And then the plot D shows the surface pressure. So the idea of like having a surface tension assisted by compression of this barrier as a function of the area that is between the barrier and the stop. So the surface pressure here is related to the force that's needed to hold the barrier in place. And as the nanowires get closer together, they're pushing back on the barrier, but you need to apply that surface pressure to get them well aligned. And we see the same type of curve that was suggested for molecules, where operating in this steep regime is necessary to get good alignment on the surface. And here are some pictures of the actual deposition of the layers on substrates. So this is after they have done the surface organization of the nanowires and withdrawn a silicon wafer from the liquid, and you can see that the wires are fairly well organized. And this is maybe the kind of packing you would expect just geometrically if you had logs on water or had a bunch of pencils on the table and just squashed them together. You know, they're overlapping, so there's nothing that's dictating they, you know, pack perfectly, but this is a pretty good density and a pretty good alignment. And I would also expect that, you know, these patterns might have a bit of swirl to them based on the conditions at which they were pushed together in the fluid, but they would generally be aligned in one direction. You can maybe kind of see that swirl in the lowest magnification image here. This is a scale of 10 microns, whereas this is a scale of 1 micron. And then they also just showed TM images of the nanowires they used that were made by a chemical method, and they had kind of faceted ends and were about of the scale of 50 to 100 nanometers in diameter. So these are single crystal silver nanowires made chemically. So one last example, which I think was a reading that was posted for the last lecture, is using a similar method to deposit graphene or graphene oxide films and organize them on the surface of a liquid and then deposit them on a substrate. And this is another recent paper which takes this classical technique and is just applying it to organization of a newer material, or a material that's now being made in larger scale. So as we discussed very briefly at the end of the synthesis, there's a lot of interest in synthesis of graphene or single sheets of carbon for things like electronic devices. And it's possible to grow graphene on metal surfaces, and it's also possible to take bulk graphite, which is made in very, very large quantities, and to chemically exfoliate it to sort of take the stacks of graphite and strip it out into individual layers. And that's the process that's used to create essentially sheets of graphene in solution. And so what they have is, you could imagine sheets of hexagonally organized carbon that have been functionalized, so they have a lot of OH groups, which makes them have a negative surface charge. And this paper talks about the balance between the electrostatic interactions between the graphene sheets sitting on the surface and other interactions in making the monolayers stable on the liquid surface. And here you see pictures of the organization of the sheets at different surface pressures, and the same idea of the sheets exerting more pressure due to their proximity and due to the electrostatic repulsive forces and the physical hindrance as the monolayer is compressed. And also see in case D where the layer has been compacted so much that in fact there are darker portions which resemble multiple layers stacking up on one another. So in principle, this is the same type of process that's happening with the nanowires or the molecules, only the geometry and the interactions between the structures are different. But this is another case where the formation of this layer is dictated by a balance of interactions. And this study used this process to deposit thin films of graphene on substrates that were both electrically conducting and transparent. So it turns out that if you have a film of these graphene plates, imagining sort of sheets of paper or large cloths arranged on a field, on a large field, if the density of the sheets is high enough such that they touch, then there will be an electrical path across the film. And that combines with the property that graphene, if it's only a few layers thick, is fairly optically transparent to create a film that's a transparent conductor. And a lot of devices, such as touchscreens, have transparent conducting layers that are used to sense, for example, the position of your finger by electrical coupling, either capacitive or resistive coupling with the surface. But you need to be able to see through the display to see what's on the real screen. So there's interest in new types of transparent conductors for those and other applications, and it's just showing that this film that they deposited by this method achieved a fairly good transmission between 95 and 100% over a broad wavelength range. So this wavelength range is between 400 and 800 nanometers, which is about the range of visible light. And I'm actually not sure if the conductivity properties of these films are compelling, but they show that they had a linear IV characteristic. So it's effectively behaving like a metal, and the transport is dominated by resistive scattering, or it follows Ohm's law due to this linear relationship. And indeed, to make new types of compelling transparent conductors, you need materials that have high transmission as well as low of electrical resistivity as possible, so having a low sheet resistance. Okay, so that concludes the discussion of monolayer deposition. And today we're going to move to techniques that combine these principles of two-dimensional assembly and adsorption in ways to make three-dimensional structures. And we're going to start with the layer-by-layer technique that essentially adsorbs monolayers sequentially to create three-dimensional architectures, and conclude with a bit about the packing of structures in 3 dimensions and the packing of microparticles and nanoparticles into single layers and into 3-dimensional structures like the ones shown at the bottom here. So then our formal topics are layer-by-layer assembly and packing into colloidal crystals. The readings that we have for today are 2 papers on layer-by-layer assembly. The first paper from Descher in 1997 is the first paper that talked about the layer-by-layer assembly method. And then the paper from Krogman and colleagues last year is a very neat approach to depositing these films by spraying, which we'll see in a few slides later on. And then the last paper discusses evaporation-induced assembly of quantum dots into nanorings using capillary forces to template the organization of semiconductor nanoparticles like the ones with different colors that we've seen so much of. And then there are a couple of extras. There's the paper from Potsiadlo, and that's from Nick Kotov's group here at U of M, discussing the fabrication of composite materials using layer-by-layer assembly, as well as there's a review paper on template-assisted self-assembly combining top-down and bottom-up approaches to specify the positions of microparticles that are assembled on substrates. And we'll see examples from most of these papers throughout the lecture today. Okay, so the first topic is what's called layer-by-layer assembly. And this is a very generic method, and you could say it's subtly simple, but the complexity is in the details, yet the simplicity and generality enables it to be very versatile for assembling a lot of different structures. And the general scheme by which the LBL method is done is, imagine you have a substrate, just like you're assembling a self-assembled monolayer, but instead of, say, dipping it in one solution and leaving it there and then just ending up with one monolayer, it's a sequential process. And for example, you take the substrate and dip it in one solution and then wait for a while, take it out, dip it in another solution that's a rinse, such as water, and then put it in a third solution and then rinse it again, and continue this process as many times as you want. And each time you complete one of these cycles, exposing the substrate to the red and the blue for the desired time, you create a multi-layer structure, what's called by this process a bilayer. And the further detail of the process is it typically relies on electrostatic interactions between oppositely charged species. So the design process is typically to start, for example, with a positively charged surface, and to put it in the first solution, which contains a negatively charged molecule. And by electrostatic attraction and this general process of adsorption, rearrangement, and desorption, if you have the right conditions and the right time, you'll end up with a desired thickness layer of this negatively charged species, here called the polyanion, adsorbed onto the positively charged surface. Then you take it out, you wash it or rinse it, and then you put it in the other solution, which has a positively charged molecule, and therefore will be attracted to the negative charges on the first layer. And you can imagine that if you're able to create two different solutions of two desired molecules or nanostructures, nanoparticles, nanotubes, graphene, whatever works, having these different charges and study the assembly process, in principle you can layer different layers one by one over and over. And not only can you do this once, but you could do AB, 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 and so on, depending on how thick you wanted the material to be. And it's the characteristics of these constituent molecules and the organization and interactions between them that are going to dictate the final characteristics of the material that you make. And it's sort of a very versatile process because in principle, the interaction of just negative and positive charges is a bit more general than what can be done with self-assembly of a monolayer on a surface or by floating of a layer of species on a liquid. And in addition to this dipping process, which is honestly quite slow, basically any way you can introduce this molecule to the surface and get it to stick will work. So we'll see examples of how this can be done by spraying as well, which is a higher throughput method than this dipping process. And indeed, the principle of this method is, like we kind of saw, that designing this amphiphilic molecule and the idea of having a thiol group held to gold with pretty much any linker you want on the end gave some versatility. The same versatility is envisioned by layer assembly, in that if you have these electrostatic interactions that hook the molecules together, if you can design the molecule of the structure to have a desired intermediate piece, whether it be a nanostructure or a molecular chain like so, you could stack up these multi-layers in a desired fashion. And this is a really idealized picture of the resulting structure, saying that they have this abrupt sort of atomically sharp interface and they're stratified like so. And we'll see that this is not always the case, but the general stratification of having the first material and the next material upon one another indeed proceeds. So as described in the general mechanism, this layer-by-layer process is governed by electrostatics and governed by having charged surfaces. So if you have your starting substrate, say it has a negative surface charge, then it's going to have a negative surface potential, just as we saw from the double layer and electrostatics in solution. After putting the positively charged molecule on it, it's going to have a positive surface potential, and then that surface potential is going to oscillate throughout the process. So indeed, here is a plot of the surface potential, in this case called the zeta potential, because that's the actual potential that's measured at the surface minus the adsorbed ions, as a function of as the process, the layer-by-layer process, is alternated. And you can see that with the specific molecules that were used in this sequence, the idea of going from positive to negative is kept, and that's actually what's going on. And so the magnitudes of the surface potentials, or the zeta potentials in this case, are about 25 millivolts, which is a typical magnitude of a surface potential that we saw for typical salt concentration in the electrostatics lecture. And also you can see that there's probably some error in this measurement, as well as some fluctuation in the actual number of molecules on the surface, but from sequence to sequence, the values of the surface potential are quite repeatable. And as I indicated a moment ago, the organization of the layers is not sort of molecularly abrupt, but is indeed stratified. And this is a plot which schematically shows the concentration of the two species in each layer as a function of position. So on the vertical axis we see the relative concentration, and on the horizontal axis we're going from the substrate surface to say the end of the film or off into the bulk. And imagine, you know, putting down the blue one first, and then the red one, and then the blue one and the red one. And you can see that because of the way the molecules diffuse into one another, imagine having two types of polymer chains that absorb, and you know, they're not going to necessarily mate like this. They might intermingle as the end of one chain kind of digs itself into a pore in the previous film. And you qualitatively end up with a structure that is both stratified and distributed. So in an ideal case, you might say, well, there's a Gaussian distribution of concentration within each layer, and at the true center of each layer, the concentration is at its maximum. You have only, say, the red molecule, and at the, quote, interface between the layers, it's not an abrupt transition, but you have a mixture of the two molecules that indeed decays. And you can imagine cases if you wanted to really create a perfectly stratified structure, maybe like a quantum superlattice, this might be bad. But if you wanted to, say, create a material that had strong interactions between the layers, such as a nanocomposite that had, you know, good load transfer in the perpendicular direction, this could actually be good because the molecules will be mixing and interacting strongly. And we'll see an example of that in a few slides. So the general principle of LBL is that this can involve, you know, people who work with it would say nearly any type of macromolecule, or, you know, large thing that you can charge and deposit, disperse in solution. So this list on the left is sort of an incomplete list of the types of things that have been deposited by LBL. And while we've only been able to see a couple of examples, there have been a lot of research and practical demonstrations on the use of this technique to make composites by, say, laying inorganic and organic materials together, as well as things like membranes for filtration, as well as surfaces that have superhydrophobic or anti-reflective properties. So taking advantage of surface texture, the ability to organize nanostructures on a surface, as well as the ability to manipulate the optical properties of surfaces by the characteristics of the individual structures. And you can also imagine if you can soak molecules into these surfaces, then by the reverse process of releasing molecules from the surface, there's also interest in using these multi-layered coatings for things like release of drugs on the surfaces of implants, or providing functionality that might prevent the absorption of proteins or fouling of the surfaces once they're put inside the body. So this is a physical picture of how LBL might be done at a very small scale, and there's a small company called Nanostrata that sells these little machines, or they call them robots actually, for LBL deposition. And what this machine consists of is it's just a box about this size, a chamber with plexiglass walls that's filled with air or an inert gas if you want. And inside it has a turntable, and that turntable has a bunch of beakers on it. And you can just put the beakers in the arrangement you want. And it has a clip that holds the substrate. The substrate would be held here. And the turntable moves up and down and rotates by desired increments to expose the substrate to the desired solution with time. So if you organize this in the sort of A, B, rinse fashion that you want, you can repeatedly expose it to the sequence that you want. And you can program this for the desired number of layers, and it can run all night, and it can put the film that you want. And this is indeed what's often used to prove this concept, to develop a new LBL composition and characterize small areas of the films. But as you can imagine, it's not very scalable, not only because the absorption time of the layers on the surface might be practically slow. It might take tens of minutes to get just that one layer. And also that, you know, if you need these big vats of liquid, you don't get a good volumetric efficiency if you have a flat substrate and a large bath of liquid. So the methods we'll see later are indeed more scalable and more practical. But one example of an LBL material made by this method, and in fact made just by dipping in these little beakers, came from Nick Kotov's group a few years ago. They're in chemical engineering, and they did a really beautiful demonstration of the design and assembly of nanocomposites consisting of polymers and clays, and they made materials that had very good mechanical properties. And this schematic is meant to show the layer-by-layer architecture of a polymer, a PVA, combined with a clay. This clay is called MTM. It has a very, very long name, and it's a naturally mined clay that is exfoliated into sheets. You can imagine it kind of like graphene, only it's a clay that contains alumina and silica and some other elements. And by doing this layer-by-layer process to create these structured layers, they were able to create the kind of like nanoscale brick and mortar architecture that we saw as kind of a biomimetic composite in the lecture on mechanical properties. And now we can compare the architecture here of the layers made by LBL to down here at the bottom right. These are SEM images that are taken of the cross-section of the composite. And we actually get an idea that there is this stratification or this anisotropy of the sheets in the planar direction. And these layers, the bilayers, are maybe 10 nanometers or less thick, so it takes a very large number of bilayers to create something that's even a film that's a few microns thick. So here in this SEM image that has a scale bar of maybe 3 microns or less, that's a 300 bilayer film. So that's something that's been dipped in this solution 300 times A/B rinse over and over again. But you can imagine making films that are thinner or thicker just by repeating this method. And their study also contains some analysis of the interactions between the polymer, PVA, and the MTM, the clay, or the organic component and the inorganic component. And they found that indeed under the conditions that they used, the material was so strong because there was actually covalent bonding between the polymer and the clay, and this was related to an aluminum atom that was coming that was on the surface of the clay and associated itself with the polymer. So it was indeed this engineering of the molecular interaction that made this material have the properties that were found. And here's some example mechanical property data from this study, and this is meant to illustrate a couple of things. First, let's compare the plot at the top right to the plot at the top left, where we see these are just classical stress-strain curves, as you might get from stretching a bar of brass. But now instead of stretching a bar of brass, they're taking one of their composite sheets and doing a tensile test on it. And at the top right, we see the characteristics of a regular polymer film, just PVA with no clay. And it has a failure stress of about 40 megapascals. And so by comparison, something like a carbon fiber is a gigapascal or higher. So this is orders of magnitude less than, you could say, a state-of-the-art composite. But when they make the film with clay plus PVA, and so bond the polymer to the clay and take advantage of the clay properties as well, you see overall the strength is much higher. In this case, the strength is about between 100 and 200 megapascals. And in the case number 2, they add another species, GA stands for glutaldehyde, which they find promotes cross-linking between the polymer and the clay, and the strength goes up by about a factor of 3. So by engineering this interaction between the polymer and the clay and architecting this nanoscale composite, they achieved about a 10-fold increase in the strength of the material. And there are other data, for example, the modulus of it and the ultimate strain before it failed. And in fact, the modulus is about 100 GPa, and the modulus of steel is about 200. Modulus of aluminum is about 70 to 80. So this is something that was as stiff as aluminum, stiffer than aluminum, and almost as stiff as steel, but in fact an inorganic material that was made by this alternate process. So that's just one, I think, of the particularly outstanding examples of how this process is used to create a new type of composite material. And we talked a moment ago about the stratification of the layers and how the molecules in different layers may interact and diffuse from one to the other. And the growth kinetics, meaning the overall thickness of this material versus time or versus the number of bilayers, may be different depending on the different materials that are at play. And this slide is meant to illustrate how the kinetics, or the overall thickness, are driven by the adsorption of the materials on the surface as well as the interactions between them. And what I want to say here is that in some cases you see a linear growth kinetic, which means the thickness is linear with the number of bilayers or with time. And in other cases, at short numbers of layers, you see an exponential growth kinetic. And what this means is that when you have a pre-existing film, say it has 5 bilayers, and you put it in the solution of the next component, not only do you absorb the new layer, the new half of a bilayer, but also the component that's in solution diffuses into the existing film and swells the pre-existing layers. So that means the more layers you have under the surface, the more of this interdiffusion and swelling of previous layers you get. So that indeed leads to an exponential dependence of the thickness on the number of bilayers in certain situations. And however, once you kind of reach saturation state, where the thickness of the film is greater than the penetration depth of this diffusion process into the existing material, then the kinetic becomes linear, but becomes linear based on having adsorption and diffusion. So this might straighten out to a line of slope like this, and this case might stay at a lower slope like this. And different polymers and different components determine whether one kinetic happens or another because of how well they organize and how well one molecule, might diffuse into another. And indeed, this study found that even though you had these clay sheets, which you could imagine are kind of like, blocking the diffusion of molecules into the pre-existing film, the polymers, because of the strength of their interactions, were actually able to snake their way down into the pre-existing layers, and that growth mode existed in this material. So moving on from the dipping method to another method of deposition of these layer by layer composites, the second paper that we'll be reading for this lecture goes through this spray method for depositing layer by layer coatings on substrates. And in this case, they chose to deposit the layer by layer coatings on fibers as a substrate that is essentially three-dimensional and also has interest for applications in filtration. And if you can take advantage of these functionalized surface coatings on, say, a membrane consisting of polymer microfibers, then you might be able to affect the transport of a gas or a liquid through this fiber mesh, for example, for, say, filtering water or for executing a catalytic process on a gas or a fuel. And so we see at the left sequential images of the process, and on the right schematics, and on the right SEM images of the fibers at different stages. And here they're depositing the LBL coating on a fiber mesh, and this is a top view and this is a side view of a cross section. And what they do is they have the same kind of like A-B system, except instead of dipping, they have sprays of the two components, conceptually red and blue, and they alternate those sprays. And I think in some cases they have a water spray which rinses them in between to achieve this layer by layer deposition. And then as the paper goes on, they also talk about depositing other coatings. The species aren't important, but in this case they're indicated orange and green by a case where instead of conformally coating the fibers, they're kind of filling the fiber with a film that connects the fibers together. And the big difference that we can see here is between the section views in the top row and the middle row, where we go from having fibers that look bare to fibers that hopefully we can discern have a distinct coating on the surface. And it's really interesting that they, even though they're spraying the liquid from one side, the hydrodynamics of the process and the fluid dynamics of it was able to coat the entire surface of this fiber. And incidentally, these fibers were made by a process called electrospinning, which basically takes a polymer solution and through an electric field creates a charged jet that can create these polymer fibers. So this is something that we'll discuss briefly next week, but it's a technique that's used to make many polymer fibers at the micro and nano scale, and it preceded the deposition of the layer by layer coatings on this substrate. So now what was in fact shown in this study is that they can create fairly linear films of their LBL coatings on these fibers. And in this case, they had a material that exhibited these linear growth kinetics, so a linear thickness versus number of bilayers. And they compared the results of their process on a flat substrate to a fiber where you in fact had a fairly similar film thickness for 50 bilayers. They were building up, I guess, a film that was about between half a micron and a micron in each case. And this is higher just because it represents the total diameter of the fiber that they were studying, so the diameter plus twice the film thickness. So this goes from 1700 to about 2500. You'd subtract 2500 from 1700 and divide by 2 to get the film thickness, and it pretty much agrees with the value we have over here for the film thickness on a flat substrate. And it turned out that the flow dynamics of the solution, the spray that they were putting into the membrane, in fact determined if they deposited a conformal layer as was desirable, or a layer which was not continuous and just had kind of this bead of material at the back surface. And they were able to relate this to the fluid dynamics of the problem, for example, by calculating the Reynolds number based on the diameter of the fiber. And this was an expression for the Reynolds number that's based on flow through a packed bed. They considered this fiber to be a packed bed of particles with a particular diameter d. But basically, the Reynolds number is proportional to the diameter of the fiber and the free stream velocity of the fluid. And so if they sprayed with a velocity that was too high, there was flow separation around the fiber, the cross-section of the fiber, and you can qualitatively relate this to the fact that flow did not reach these areas of the fiber on the back, and indeed formed just this bead because of the separation flow recirculating and hitting the back surface. But if they did the deposition with a slower velocity and a lower Reynolds number, the flow did not separate off the fiber, and it deposited relatively conformally around the surface. And these are the conditions, these lower velocity conditions or lower spray flow rate, that resulted in conformal coating of the fibers like so. And this is pretty cool because it happens even though the fibers are fairly well packed. And an issue beyond this that you'll read about in the paper is that in spite this process work, it only works to a certain penetration depth within the fabric, because you can imagine the flow gets more physically obstructed as you get farther into the fabric, and also the spray gets blocked and the precursor gets consumed. But this was the way that they achieved conformal coating of cylinders, by this directional flow process. And there have been a number of other examples of using this to coat interesting geometries. Here we just see the case of coating spheres by dipping LBL, and these are optical images of coating spheres with multi-layers, which appear to contain some type of nanoparticles and a polymer. And by the number of layers deposited on the sphere, we're plotting the integrated intensity from these images. And you see that it scales with the square of the particle size, or the layer number, if you can relate the layer number to the radius, because we're depositing a material with greater area as the sphere gets bigger. And this is just schematically showing, like, if you were to be able to tear through the layers on this sphere, you would see that you would have multiple stratifications, and the number of them would increase as the particle got larger. And one further take on this deposition on spheres and perhaps other circular geometries is the process to do the layer-by-layer assembly, say on a polymer sphere, and then perhaps dissolve the sphere, and then you would end up with a shell which might have submicron thickness that would be hollow inside. And this is a fluorescence image where the LBL process deposited a molecule, a fluorescent molecule. It could be a quantum dot or it could be a fluorescent protein on the surface of the sphere. They dissolved the sphere, and then the sphere actually collapsed in one part. So it dented in like that, and that's why we see the funny shape like this. And there's, in fact, a company I think based in Germany, that's developing LBL coatings for a lot of these applications, particularly these layer-by-layer coated spheres. And one of their specific applications is, say, coating the spheres with fluorescent molecules or quantum dots having different colors, and combining that with, say, functional groups that might bind to particular biomolecules in the body, and using those for the purpose of high contrast imaging. So having this microparticle that will stick to a particular biosurface and using that to create a colorful image of where that molecule exists. And the picture on the right is showing another possible use, and instead of incorporating things like fluorescent molecules, they're actually incorporating metal nanoparticles, magnetic nanoparticles in particular, which will serve as contrast agents for MRI, for magnetic resonance imaging. So likewise, injecting a functionalized set of these spheres, and if they adsorb to particular tissues or places inside the body, then you would get a high contrast image in the MRI. And ideally, these could then be flushed outside of the body at a later time. So they wouldn't be persistent for a long time, but it would assist in imaging. And that's one of the applications that they're commercializing that rests upon this technology. So as you might imagine, there are some other ways of scaling up this process. In principle, you could also do it on a roll-to-roll fashion if you had a flat substrate film and had containers of the different solutions organized in a sequence. Then you could put it in, say, the first component. This one is PAH, and then rinse it for the desired time. So in this case, there might be 3 rinse baths necessary to give the appropriate rinse time. And then you could bring it through the second component, the PAA in this case, and these may be at different pHs, which also would control the charge in solution, and then rinse it again. And you could have this fairly large web that's drawn through these different buckets and achieve coating on a more continuous and large-scale basis. And in fact, this is exactly what's been done in this machine, which I think is an example from a company in Japan where they're coating essentially a paper substrate or generally a thin film by sequential LBL, by dipping the paper into different different baths of desired solution. So some of these are probably the rinse, and some are the desired A and B components. And it also appears that the film goes up and down a couple times, and up and down again. And what's probably happening up here is they're drying the film after the rinse step, so it's ready for the subsequent film deposition. So this probably takes this film and takes it through the desired number of coatings and then collects it on a roll and uses it for a particular application. And that application was to coat the inside of bags with a multi-layer film by the LBL method that will actually release ethylene into the bag. And if you have fruit inside the bag, there are certain fruits whose rate of ripening slows if you have a small concentration of ethylene in the environment. So they used the LBL method to deposit a film containing what's said here to be an enzyme that's extracted from a bamboo plant, and that was used to, over time, release ethylene into the bag, and that made these fruits last longer. So I don't know, it looks like there's a cantaloupe here. I don't know what fruits respond to ethylene better than others, but I think, for example, bananas that are known to ripen quickly are often shipped in trucks that contain ethylene, and ethylene prevents the ripening. And it seems that the LBL method was used in this case to release a bit of that molecule by a time process for this sort of application. And that was done about 10 years ago. And another application that Descher talks about, and this was from a presentation of his that I found, is the coating of contact lenses. So you can imagine that that contact lenses require a bunch of coatings to prevent them from irritating your eye and to make them clean better. So contact lens solution, or the surfaces of contact lenses, are indeed also sometimes made by LBL method of particular molecules. Okay, so that's the end of the discussion of LBL. Are there any questions or comments? So the final topic for today, and the subject of the rest of the slides, is the use of capillary forces to assemble micro and nanoparticles. And you can imagine that in the methods we've talked about so far, layer by layer assembly, Langmuir-Blodgett, and use of self-assembled monolayers, in all those cases, there's the immersion and withdrawal of a substrate from a liquid solution. And so there is, in fact, a meniscus that may or may not play a role in the way the molecules end up in their final configuration. And here we're not going to directly apply this to any of the previous methods, but we're going to see how capillary forces, or the basically forces induced by the shape and size of the liquid meniscus between, for example, two spherical particles, can be used to achieve ordered packing of micro and nanostructures. And then in Monday's lecture, a week from today, we'll try to expand upon this example to understand the balances of different forces. For example, capillary forces and other forces that might be applied externally to manipulate the balance of interactions among structures. So the figure at the top left here is just a schematic example of how, if you have a droplet of solution that, say, contains polymer microspheres. So imagine these as beads of polymer that might be 1 micron or 500 nanometers in diameter, and they are charged and dispersed in solution. If you have, say, a silicon substrate and take a droplet of that solution, drop it on the substrate, and then wait for the liquid to evaporate, you'll find that there are places, if you look at the material afterwards, where the particles have been packed very well. And it turns out that as the liquid dries and the meniscus withdraws away from the edge of the droplet, a few things are happening, and a couple important things are happening, in that as the liquid dries, there are attractive capillary forces caused by the recession of the meniscus down in between the two particles. And this leads to a lateral capillary force that pulls the particles toward each other. And you can imagine if the particles have enough mobility and thermal energy, it might be possible to pull them so they're packed like you might think about packing oranges or ping pong balls on the table. And that's actually what happens. And also the circulation that occurs in the liquid as the meniscus is moving away creates a convective flux that kind of resupplies more particles to this interface. And we can imagine that the humidity of the atmosphere, or the concentration of particles in the system, or the temperature, which might dictate how much thermal energy and how much thermal rotation is in the flow, are all going to affect this process. But in principle, if you take pretty much any solution of nano or microparticles that are sufficiently monodisperse, and you dry a droplet somewhere near the edges, you're going to see well-packed layers. And one of the things we'll get to more next time is how these forces scale with separation. And one of the things that benefits the use of capillary forces to assemble components at small scales is that the strength of the force between, say, two objects that are separated by a meniscus generally scales with an inverse power to the separation, or an inverse power to essentially the curvature, which is related to the separation between the two surfaces. So we don't need to study the details of this curve itself, but it's showing a computation of the normalized force existing between two plates as a function of their separation, and the force resulting from the capillary attraction due to the surface tension within this gap. And this is going to depend on the contact angles and the surface energies. And if you're considering assembly of particles, it's also going to depend on the density difference between the particles. There's a big difference that the particles are a lot lighter than the fluid than heavier than the fluid. But this basic principle of using lateral capillary forces to pull things together is pretty versatile, and we'll see a number of examples of how this is applied. So if you wanted to deposit particles from solution onto a surface and try to control this self-organization, you could basically think about trying it in a number of different ways. Pretty much any configuration of liquid and surface that lets you evaporate from the meniscus. But in particular instances, how you configure the meniscus and control the rate of evaporation and the configuration of evaporation might affect how the process proceeds. So this is a schematic from a really nice PhD thesis from ETH Zurich in 2007, which I'm sure you can find online just by searching this name, and showing, for example, the process of coating particles on a substrate by dip coating. So not really like Langmuir-Blodgett method, but having a solution of particles and withdrawing the substrate out of the solution. So you then organize the particles on the surface that's moving vertically. So here, while if you have a droplet drawing on the substrate, the motion of the meniscus might be less controlled and less spatially uniform. If you're able to move your vertical surface at a controlled rate, you might be able to control the rate at which the liquid tries to stack these particles down vertically on the surface. Likewise, you might also deposit a drop on a surface that's inclined or a surface that's flat, and combinations of the evaporative forces and the gravitational flow of the liquid down this angle might also affect the assembly. And in another case, you may want to induce rapid liquid motion, for example, by spin coating, or here you might take your silicon substrate and put it on a spin coater, so basically a turntable that spins at anywhere from tens to thousands of RPM, and then understand how the particles might pack as the liquid flows outward from the center. And because of the centripetal forces as the substrate is spinned, you can imagine the liquid is carried outward. And now the process is happening at a much more rapid rate than in droplet drying because the spinning is taking the meniscus away. And we'll see a couple of examples of this case in a minute. So here's a case of depositing these polymer particles on flat surfaces. So in this case, we're looking at 2-micron diameter polymer particles on glass slides, so just regular glass microscope slides. And these were deposited by the method of spin coating, by taking a droplet and putting it on a spinning surface and spinning it up and letting the liquid fly to the outsides. And these are just 2 data points, but here we see the kind of effect of the spin speed or the rate of the meniscus motion on the degree of packing in this layer. So in the bottom right case with a lower spin speed, there was, you could say, more time for the layer to become well packed. And although in both cases you have these sort of separated domains, kind of like particle grains, here the domains are much larger in the bottom right case than in the top left case. You may say that you moved the same amount of liquid over the surface in both cases, but in the top left case you moved it too quickly and didn't give enough time for the particles to reach a more highly ordered state. And it's possible to do this over very large areas. You can imagine doing it over a whole wafer or over big sheets if you're withdrawing them out of solution. But by and large, the size of the domains that you achieve is quite limited. And these are ways where things like templating can do better to achieve long-range order. Or specific studies of the dynamics of assembly could perhaps try to understand how to prevent formation of these defects. And this is a plot from that thesis that just shows some different conditions that resulted from, for example, varying the spin speed in the deposition process and varying the concentration of particles in the solution. So if you vary the spin speed, in this case we're going from 100 RPM to having, say, 600 RPM, so a factor of 60. You can imagine that at low spin speed for a particular concentration, then you might have better packing of the particles, but you're not going to throw the particles off fast enough, so you would have more layers than you would in the case of a high spin speed. So we see here at this high concentration of particles, increasing the spin speed went from multi-layer structures to eventually having single-layer structures. And here he's not really talking about the specific packing, but just in the number of layers that resulted. So faster spin speed took the particles away more quickly. If you go down in concentration at the same spin speed, you saw, for example, that the number of layers also decreased. And in the case of having a much smaller concentration, only 1% of the particles at this spin speed of 100 RPM, he achieved monolayers, but at lower speeds, he achieved incomplete monolayers, meaning there weren't enough particles, or the particles were taken away too fast, and these resemble large gaps between the domains. So when it's said that there's a monolayer here, it means that you have fairly tight two-dimensional packing of the particles, but there are these individual domains with defects, or analogous to dislocations. And when you have incomplete monolayers, it means you have a substrate with just groups of particles that are isolated from other groups of particles. And then if you have too many particles in the system, or you're not taking them away fast enough, then you end up with essentially heaps of structures. And in some cases, you may want to build these three-dimensional crystals, and in other cases, you may want to keep it to one monolayer. And one case that we've seen already that showed a possible application of having individual monolayers or double monolayers of these assembled microparticles was to use them as a shadow mask for deposition of metal in this process developed at Northwestern, which is called nanosphere lithography, or you could also say microsphere lithography. And here we can just see, to recap this slide, that now, for example, by depositing these ordered polymer particle layers by evaporation, you could achieve good packing of the spheres. And then if the spheres are well packed, then the interstitial spaces that are visible to below will have this triangular shape, and then they can be used to, for example, deposit triangles of metal. And if you assemble the spheres, deposit metal by evaporation or sputtering, and then remove the particles, then you end up with these arrays of triangles that have interesting optical properties because of their shape and because of their proximity to one another. And if this process that gave a monolayer was repeated to give another monolayer on top of the first layer, then you created interstitial spaces that were smaller and only half as frequent. So in the same area that you'd have 6, in the first case you only have 3, and they're more like dots rather than triangles. And you can see here that this was a case where they used fairly good control of this assembly process to achieve a well-packed domain, and this gave very good organization of the particles within these domains. But I would expect that if you zoomed out in the microscope, you would see that this good order extended only over a relatively limited range. And also, for example, the registry of the particles with respect to the substrate, say the rotation of this lattice, was also not prescribed by the conditions. These could pack in pretty much any direction as desired, but once they started packing in a domain, the packing would proceed pretty well. And here are the kinds of results that we discussed earlier using these particles, for example, just showing that the shape of the particles, in this case controlled by the double layer process versus the single layer process, and their thickness and their spacing had a big effect on the plasmon resonance frequency relating to the characteristics of the assembly process. So you can imagine that the desire to create large arrays of these particles and to create them very precisely is intimately tied to the ability to organize the particles in very controlled ways. And there are also fairly elegant and successful methods that have been used to template the packing of spheres geometrically. So now we can take a principle of creating cavities, such as by photolithography or e-beam lithography, and relate the size of those cavities to the expected ability of spheres to fit inside the cavities upon this evaporative assembly process. So the schematic at the top is showing a case where these researchers had 2 glass slides separated by a distance of about 30 microns. And on one of the glass slides, they had patterned a photoresist, and the height of this pattern was maybe a couple of microns, and the width of this holes was also about a couple of microns. And when they took a solution of polystyrene spheres in water and passed it through the gap between these glass slides, the interactions between the spheres and the glass were such that they stuck in these cavities. And indeed, what they studied was how the size of the cavities related to the ability of particles of a certain size to pack. So in this case, when they had particles of 1 diameter, small d, and a cavity of a larger diameter, within a certain size range, it was found that they were able to pack trimers, or clusters of 3 particles inside this hole. And you can see that also that the orientation of, while there are always 3 spheres in a hole, the orientation of the triangle is not always the same. Sometimes it goes one way and sometimes it goes the other way, and also the angle is not the same. The orientation might be slightly preferred based on the evaporation of the liquid, but that would depend on a lot of different conditions. But this is a pretty good success in taking advantage of this geometric constraint to pack the structures in the holes. And in fact, this study was expanded to show the kind of generality of this method, and with good control of the liquid flow and so on. What they showed is that you can geometrically relate simply the shape and size of the template to the resulting packing that occurs. So, for example, if you had particles with diameter d that say there's 1 micron in diameter or 1 unit in diameter, if you had a cavity that is between 1 and 2 microns in diameter, then you'll only get 1 particle in the hole because another particle won't fit. Also, of course, the depth of the hole is between half a particle high and 1 particle high. It's not deeper enough to hold 2 particles. And then if you expand the hole a bit larger, such that its diameter is between 2 and 2.15 times the diameter of the sphere, then you get preferentially 2 particles in it that are packed, in a kind of a lateral stack like so. And then if you go slightly bigger, then you get 3 particles, slightly bigger and 4 particles, and 5 and 6 and so on. And also can get more interesting multi-layer structures by the tendency of particles to pack at interstitial sites on previously assembled layers. And you can imagine the ability to execute this process depends very much on the precision and dimensional limits of the lithography process. So if, for example, you wanted to pack particles that had a 500 nanometer diameter and wanted to discriminate between the assembly of dimers and trimers, then this nominal width would be 2 times 500 nanometers, so 1 micron. That would mean that you'd need to control the lithography process within the hundreds of nanometers range. So this is something that is really at the limits of optical lithography to even create structures that can pack small numbers of particles that are really in the micron range. And different things by patterning rows and triangles and rings and so on. And they have a lot other cool pictures in the paper stacking things zigzag and kind of making helical structures. But I just want to emphasize that this principle of geometric compatibility indeed extends to the assembly of these structures. And you could perhaps take some kind of kinematic principles like of precision and say imagining putting like balls in grooves or balls in holes as we might use for assembling large optical components, and the same kinds of things are at work here. And in moving from 2-dimensional to 3-dimensional structures, there's really nothing different between the process of creating 2-dimensional layers and creating 3-dimensional packing, other than you let the process proceed and provide conditions that let the particles stack with one row upon another. And if in the 2-dimensional case we considered planar defects, in the 3-dimensional case we consider 3-dimensional grains. There would be chunks of particles that have 3-dimensionality rather than 2-dimensionality. And as you also might imagine, a further step on packing 2-dimensional layers is packing with one type of particle is packing structures with multiple types of particles. So these are just schematically showing the ability to pack 2 different sizes of polymer particles. For example, taking 0.991 micron size PMMA polymer spheres and packing them with silica spheres that have a size that's slightly smaller, about 0.6 microns. And in fact, an additional aspect of the process of the results shown here is that the particles had opposite charges. And the fact that the PMMA particles were positively charged and the silica particles were negatively charged influenced their packing into what looks to us kind of like a crystal lattice. And we're just seeing them red and green in these actual images because they had coated them with fluorescent molecules that appeared red and green and let them view the packing under these individual cases. And this same principle has been extended to superlattices of nanoparticles. So at the micro scale, when working with, say, polymer and oxide spheres of, say, 100 nanometers or bigger, people often call them colloidal crystals. And in the case of nanoparticles, they're often called superlattices, but structurally they're the same. And here we just see some examples from a paper a few years ago by Shevchenko and colleagues that studied this type of process for assembling different nanoparticles of different materials. And here we can see that they're putting particles such as iron oxide and gold together, and lead, selenium, and other particles. And we don't concern ourselves with the details, but suffice to say, this principle of packing spheres together of different sizes and shapes is relatively general and will relate to the conditions of evaporation and assembly at the particular sizes. And there's a certain ability based on the relative sizes of the particles and their interactions to achieve different crystalline packing. So this structure, these aren't sodium and chloride particles, but it's meant to, they're using sodium chloride because this packing is resembling the cubic structure of the real lattice of sodium and chlorine. So you don't have sodium and chlorine ions here, but you have nanoparticles of different sizes that assemble themselves into the cubic lattice, which is seen at the atomic scale for sodium and chlorine. And all these examples here refer to the types of lattices that are seen by packing of these structures. And another very important consideration that hasn't been shown in any of these results is that the monodispersity of the particles you start with is very important. And it's been shown by experiment and simulation that the standard deviation in diameter needs to be about 5% or less to get good packing of these structures. So the ability to synthesize very monodispersed nanoparticles is essential to get this type of packing. And for example, if you can't make a certain material monodispersed within a certain size range, you pretty much can't achieve this degree of packing as shown here. And so as a corollary, for example, the self-assembly of these polymer microspheres has been studied very widely, but there aren't many good synthesis processes that can create highly monodispersed polystyrene particles beneath a diameter of, say, 200 nanometers. So as a result, there hasn't been a lot of success in packing polymer spheres having diameters less than 200 nanometers. And one big key in the work shown here is the ability of this research group to also make highly monodispersed solutions of, for example, iron oxide particles or gold particles, such that they can get them to pack in this interesting and ordered fashion. And we just have a couple minutes left, so these are the last two slides. And to set things up for next time, I wanted to show another take on templated self-assembly, kind of combining the self-assembly of microparticles and nanoparticles and using the summation of a few different types of interactions. So at the top left is a schematic from a recent paper that does a two-step process. They first mix a solution of polymer microparticles and semiconducting nanoparticles, in this case cadmium selenide quantum dots, and they do this evaporative self-assembly and find that two things happen simultaneously. First, the microparticles pack into monolayers as we expected, and second, after the liquid kind of recedes beneath the space between conjoining microparticles, the meniscus does another thing. It takes the nanoparticles down into the crevice under each microparticle and evaporates them to form a ring. And so here on the right side, we say AFM images of the rings that are formed by executing this process with polystyrene spheres of different diameters. And you can see that the height and the width of these rings, or the diameter of these rings, generally scales with the diameter of the sphere that is used to create the template. So here, with a 200 nanometer sphere, there was a ring of about 85 nanometers, which is going to be determined by the de-wetting of this solution underneath the cover of this microparticle. And so they did the assembly process and then took a piece of tape actually and peeled away the polymer spheres, and we're left with these self-assembled rings. And what we'll get into next time is a more rigorous consideration to close this topic of the balances between forces in these considerations. And the paper talks about how the geometry, the size of the quantum dot, and its size in proximity to the particle, for example, thickness of the organic coating, the monolayer and/or surfactant that's assembled on the particle plays a role, as well as the balance of forces in this situation. For example, as we saw today, you have capillary forces that draw the particles together, and you also have adhesion forces between the nanoparticle and the substrate, and between the nanoparticle and the microparticle. And also there are double layer forces, electrostatic repulsion, that cause the particles to want to repel each other. So it's effectively a balance of these forces, or the forces being forced in a certain regime that facilitates organized assembly by this template. And you can imagine that the influence of these different forces is much different on a particle, a nanoparticle, than it is a microparticle, and that also plays an important role in these types of assemblies. So that's all for today, and we'll see you next Monday. And although I'll be away this week, feel free to send me email if you have any questions about things for the project as you're getting started. I want to make sure you all get started and get to be looking into your topics in good depth before we meet next time.